Hello and welcome to this introduction of UDAVA, or Unsupervised Learning for Data Validation. UDAVA performs unsupervised anomaly detection and discovery of process behavior patterns. To understand how this is done, let's take a look at a high-level view of the tool. UDAVA takes as input sensor data coming from one or more reference production cycles during repetitive manufacturing. During this first step, pre-processing, this time series is divided into subsequences of a given size, and from each subsequence we compute a feature vector. This feature vector consists of a selection of statistical properties. In cases where we have knowledge about the sensor data, for example about different sub-processes that occurs during each cycle, this can be annotated on the time series and provided as extra input to the pipeline. The annotations will be used to initialize the cluster centers and helps the algorithm figure out the most meaningful clusters. When we have computed all feature vectors, we use a clustering algorithm, for example k-means clustering, to create a model. This model is then used on new production data by continuously computing feature vectors and using the model to assign each subsequence to the correct cluster. We also compute a deviation metric for each feature vector and subsequence based on the sum of distances between the cluster centers and a given feature vector. This deviation metric indicates whether a subsequence is conformal to what the model has seen in the reference or training dataset and helps us detect anomalies. After production data has been labeled and validated, we merge continuous sequences of labels into segments. Very short segments can be filtered out as noise by setting a threshold for minimum duration. After the filtering, the pipeline outputs an event log which describes the start and stop of each segment. This enables us to discover and validate repeating behaviors over time. We use an open source tool called Label Studio to create the annotations. In this example, we have uploaded time series of the grinding power during one production cycle of a grinding machine. The production cycle consists of 7 different types of sub-processes, and we have labeled each of these using Label Studio's time series annotation tool. These annotations can be exported in JSON format and used directly as input to UDAVA. The UDAVA tool is developed in Python and can be run locally by running a server script. The tool is used through a user interface in the browser. To create a model, we choose the first tab. We are provided with 2 options, either filling out a form with configuration parameters or uploading a parameters file. We choose to upload this file in a YAML format. In the parameter file, we specify the name of the folder where our dataset resides and the name of the variable that we are analyzing. We will in this example also use the annotations I just showed you, and we must therefore specify the folder where the annotations are. As mentioned, these production cycles consist of 7 sub-processes, which is why we also specify that we want to have 7 clusters. We go back to the user interface and upload the parameters file to UDAVA. And after a few seconds or minutes, depending on the size of the dataset, we can see that the new cluster model appears in the model dashboard. In this dashboard, we can also see which dataset and variable we used for each of the models, and by hovering over the number of clusters, we also get details about each cluster the model has made. Since we used annotated data with the name of each sub-process, we also get this name as a part of the cluster information, along with some statistical properties. To use the model we just created, we go to the Inference tab. Here we have to put in the model identifier and then upload the dataset we want to run inference on. We also want to plot the results. The plot appears below, where the time series data have been labeled according to which cluster each subsequence belongs to. The colors correspond to the information given about the clusters in the model dashboard. The deviation metric is also shown in black and indicate areas with larger deviation from the reference data. The Inference API can also be accessed through the command line, which means that we can interact with it using automated scripts for processing sensor data. The input should be provided in JSON format and needs to include the model ID, the name of the input columns, and the data itself. We can pass this to the API using a post command like this. UDAVA will then process this data and return the results in a JSON format. The JSON output includes the timestamp, the cluster label, and the deviation metric. UDAVA is containerized using Docker technology. To build the container, we run this command. This will ensure that all the required dependencies are installed inside the container. To run the container, we use this command. It will set up 2 Docker volumes that are connected to directories on the host machine. This will ensure that the assets created by the pipeline are saved persistently on the host and does not disappear when we close the container. The command also exposes a port from the container, which makes it possible to connect both to the web interface and the API. When we run the command, the Python Flask server will automatically start. Thank you for listening to this introduction of UDAVA. More information can be found on the GitHub page of our tool.